Uh, okay, welcome to seminar Geometry, Arithmetic, and Differential Equations of Periods. So today it's a great honor for us to have Sergei Yakovenko, who is going to talk about how transcendental are periods. Okay, Sergei, go ahead.
Thank you very much, Hussein. I always like to visit Rio in person. Hopefully, we'll do this soon again. But for the moment, it's a great thing to see your faces in this metrics of in this period metrics, I would say. So I guess that periods, the word period, is something that is responsible for one of the letters in the abbreviation GADAP, right? Uh, in this abbreviation, P stands for periods.
Yeah, of course. And since it is plural, actually, in the
okay, so well, I will talk about lots of periods actually. So, what is a period for me? Because different people try to understand different things. I will restrict myself to the simplest, the most basic situation. So we have an algebraic, an algebraic curve, which is a planar affine curve. And this planar affine curve is a Riemann surface, so we may choose a one cycle on it. So initially, I would say that the situation was assumed to be real. So we have a real algebraic curve, and delta is one of the ovals of this algebraic curve. Now take another ingredient, take a polynomial differential one form on C2. Once again, it was initially assumed to be with real coefficients. And then the period, by definition, is the integral. Well, just the usual pairing. You take the form and integrate it. So this will be a number, and this number, well, it's called by lots of different names. In particular, in theory of foliations and differential equations, it is called a complete abelian integral. Completeness means that we integrate over the cycle and not for a open arc on the Riemann surface. So this period, as follows from its definition, is actually depending on two geometric arguments. That's the cycle itself and the form. And each geometric argument can be parameterized by a couple of say, complex numbers. So for instance, we can always assume that the algebraic curve is defined by a polynomial equation with the with zero at the right hand side of the equation, and the coefficients hij are coefficients of this polynomial equation. And since the equation is homogeneous, so we see that polynomial curves like this are parameterized by points of a projective space of large dimension. And for the same reason, we can take a polynomial form, and it will be parameterized by some complex affine space, linear space of appropriate dimension. So we have, in fact, not just one single number, but a function of multiple arguments, actually two geometric arguments, and so two groups of complex arguments, one projective, one linear. And well, dependence on the form is linear. And so this is the easy part to study. What is much more difficult is how this period depends on the curve, which is, okay, as we know, curves might degenerate and so be singular, and for some curves it's not clear how you define cycles, whether they can pass through infinity, and so on and so forth. So, but generically, and I stress here generically, an affine curve is a smooth curve transversal to the infinite line. And we know by classical theorems that this curve has genus like this after compactification, projective compactification. And because of the points at infinity, we need to to add also a few small loops around the punctures at infinity. So altogether, the homology has rank d square. And what we can do is we can introduce a frame in the homology group. That's how we do it. We pick a generic curve. We choose a collection of linear independent cycles on it, and then we can continue them. This continuity holds as long as what means continue by continuity, we deform curve, and as long as the deformation allows us to track all cycles, we can push them from one point to another. And so we have a multi-valued framing actually on the space of generic curves. Multi-valued means that if you make a continuous deformation and restore the curve back to its original position, the impact of this on the cycles can be non-trivial. And in the same way, we can choose a basis in the differential forms. That we consider d square differential two forms. And for each one, we took say a monomial, well, I wrote pre-images, it should be primitives. So, and of course, as long as I choose one primitive instead of the other, the period will be the same. So we have equal number of cycles and forms, and then we can form the period matrix, which is multivalued analytic d square times d square matrix function, Remy on CPN, on the space of all algebraic curves, which is ramified and invertible over some projective hypersurface, a divisor, which corresponds to bed curves, or rather bed configurations, bed pairs, gamma, delta. The problems may arise from two reasons. One reason is that the curve itself becomes singular, and the simplest singularity is, for instance, appearance of a normal self-intersection, a normal crossing on the curve. But even
Sergei, are you considering the Gelfand-Leray of these forms, because there are two forms integrating over one cycle?
No. I take primitives.
Okay.
So of course, at a certain moment when I compute the Gelfand-Leray derivatives, I would have to take d omegas over dh, and then that's why I've chosen monomial forms, primitives of the monomial forms. So, well, going back to the singular locus over which the period matrix is ill-defined, well, you may happen that over some particular curves, monomial forms, primitives become linear dependent. And so your period matrix degenerates. And I want to consider only points, only curves gamma for which it is non-degenerate. Now, having defined this this notion of period matrix, we can write down what is called a Picard-Fuchs and also a Gauss-Manin system. So this is a system of first-order differential equations in Pfaffian form, which explain how the the period matrix behaves. So we to write this system, we note that for any path, so we take a say a projective space. We take a path gamma 0, and then we continue a period matrix around some path gamma in such a way that it avoids a bad divisor sigma, bad polar like this. Then what happens with the period matrix? Well, the forms will, of course, go back to their initial positions because they are globally defined and have no singularities. But the cycles can undergo a non-trivial transformation, which is called the topological monodromy. And the topological monodromy means that the matrix of periods gets multiplied from the right by a constant matrix, which is called the monodromy matrix. This constant matrix depends only on the topology of the singular divisor inside the projective space of all systems of a given degree. So it is something quite specific and regular and can be studied, and of course was studied intensively. Now, what happens if we consider, instead of the matrix X, we consider matrix dx? So it does mean that I just take a differential, exterior differential of every matrix element of my period matrix. And of course, if I look at this formula, I see that dx will be, after continuation, dx will be dx times the same constant matrix M gamma, which means that once I form a logarithmic derivative like this, both gamma, M gamma, and M gamma inverse will cancel each other, and therefore we have a single valued matrix one form on CPN, which is well defined outside of sigma. And since the period matrix can grow at most moderately, that's polynomially, when we approach the singular divisor, it will have at most a pole on the singular locus sigma. So we have a rational matrix function, and its degree can be easily computed from all the data that we have. So again, I won't stop on the calculation. And this system is called the Picard-Fuchs system of Pfaffian equations. So we all of a sudden, we change the point of view, and we consider, instead of solution, we consider a system of equations which is satisfied by this solution. And a few things we know immediately from this construction. So first, we know that not all systems of Pfaffian equations have solutions. There is an integrability condition which ensures that the local solution exists. This integrability condition takes the form of zero curvature condition, so that the Gauss-Manin condition is locally flat. It has zero curvature, and in differential language, it follows that it's formulated like this differential condition. But we know that it is automatically satisfied because we started from the solution and got over the system. And of course, we know that as we approach the singular divisor, the period matrix grows tamely, polynomially, which is a very characteristic restriction, because in theory of differential equations, we have a dichotomy, a typical dichotomy, that the growth can be either moderate, like a pole, or exponential, which corresponds to essential singularity for functions of complex variable. And now I want to formulate the goal. What do I want to know? What do I want to be able to tell about such systems? So as before, we have the equation dx is equal to omega x. Omega is a rational function of gamma, which is itself a point on the CP M large space. And I want to count zeros. But what means to count zeros? You can count zeros of a scalar function of one variable. That's what you can do unless the number of zeros is infinite. So we have here it's a different situation. So first we have not one function, but d square of them. We have not one independent variable, but the whole bunch of them. We have the projective space. And we have to face the problem of multivaluedness, because even if we somehow manage to reduce things to one dimension, we would have to choose branches of analytic functions so that we would be able to count their zeros. So we do this in the most a straightforward way. So in order to deal with the fact that we have the range space of matrices more than one dimensional, what we do, we just consider all non-trivial linear combinations of the matrix entries. And we consider not one function, but we want to find bounds uniform over all such combinations. Why linear combination? Well, that's only natural because well, the range is a linear space, and it is it's natural to consider only linear combinations. To deal with the problem that the dimension of the source space is greater than one, so what I do is I just take all possible one-dimensional projective lines. So I can arrange them in pencils so that all of them pass through the same point. I can consider all of them independently, but in practice, what I want to do is I want to consider a restriction of my functions from the first item here on all such projective lines. Well, I cannot do this for all such lines because some of them are inside the singular locus. Singular locus is high dimensional, and of course, it can contain entirely some projective lines. What I do is I simply ignore them. I consider only lines that cross the singular locus by isolated points. And then, because I know the degree of this locus, I know the maximum number of singularities. And to deal with the ramifications inside of each projective line, I choose a triangle. Why triangle? First, because it's simply connected. And therefore, inside each triangle, I can choose no branch of functions. If I choose a different branch, actually, I will just get a different function from this linear combination. So if I get bounds for the numbers of zeros that would be uniform, then all will be covered. And the question is why I need triangles, because if I have a singular point here, say A, on my projective line, I need to choose a simply connected domain, but I do want this domain to stay on one sheet of the Riemann surface. So I need to exclude domains which will be spiraling around my singular point. A spiraling domain is an illegal situation. I can give immediate examples showing that you can count the number of zeros on each floor of the Riemann surface. But if you have an infinite staircase, then you can easily get an infinite number of zeros that actually never coincide with each other, coexist with each other. And so what we have is now I define the uniform bound, which is supremum over all elements of this construction. So I take all linear combinations, restrict them on all projective lines. I consider a restriction on all triangles which are free from the singular locus, but eventually having singularities at their boundary. So the singular point may well be on the boundary of a triangle, on its side, on its vertex. So all this is legitimate. I want to have a uniform upper bound. And then if this uniform upper bound exists, I say that my problem has finite solution. And if I can compute this upper bound, I would say that this will be the answer to the problem of counting zeros. So what is the motivation for such a strange formulation? So here is just a very brief reminder. So probably I will just a few words say that it came from the Hilbert 16th problem, which asks about the number of limit cycles of a polynomial differential equation on the plane. This problem is hopeless still now, so there is no even most fundamental uniformness result. So for the moment, we know that only this number is finite for any specific differential equation. But we can consider different relaxed cases. So for instance, we can consider a Hamiltonian a differential equation. Here it is when the form alpha is the derivative, the differential of a Hamiltonian. This differential equation is conservative, so it has no limit cycles. All closed trajectories are appear in non-isolated families. But if we apply perturbation epsilon omega with small epsilon, then we introduce a small dissipation, and so most of those trajectories would typically become spirals going in one or another direction. And in order to answer the question, when a closed trajectory of a conservative system evolves into, generates after bifurcation a limit size, we need to consider the Poincaré-Pendragon Melnikov integral, which is just the dissipation of the perturbation over the period. So if it is non-zero, then such periodic motion cannot survive in the perturbation as a periodic motion. If it does, then under some easy assumptions, you should prove that this indeed generates a limit cycle. So there was formulated an infinitesimal Hilbert problem. So was it formulated by Arnold, Ilyashenko? It's now a matter of ancient recollections, because of course nobody this formulation was coined after quite some time of a force, when it became clear what does not work with the initial system. But still, this was the main motivation for the study of periods for us. Now, as I told you, the monodromy of the Picard-Fuchs system is determined by the topology of the bundle of smooth algebraic curves over the projective space. So and for any small curve around this singular locus, we can, with this curve, we can associate the monodromy matrix, which I already said was M gamma. And we have the following definition. So we will need special property of this monodromy group, which is called quasi-unipotence. Quasi-unipotence means that all those matrices have eigenvalues only as roots of unity. Actually, we need a weaker assumption that they are on the unit circle. So the question is how you verify this. And the key tool here is the Kashivara theorem, which says that you need to verify this only for small loops around main components, principal strata of the singular locus. Singular locus is an algebraic variety, so it can be stratified. It consists from the smooth parts of the divisor and also eventually some very degenerate points where you have no smoothness. And theoretically, I would say it would be difficult to say whether this condition is true for a small loop around a very degenerate point. The Kashivara theorem says that we don't have to worry. If we can check this condition for small loops around the principal components, then we are set. And now I just have to recall you what means a small loop around the principal components. The principal strata, as I said, corresponds to a least degenerate affine curve, which has only one normal crossing. If you perturb such a curve, and that's the meaning of a small loop around it, you will get a situation in which a singularity of the form x squared plus y squared is perturbed by a small term, say rho. And what happens with the monodromy is well known. That's the Picard-Lefschetz, formula, which shows that at such a point you have a vanishing cycle, and a small monodromy around the curve corresponds to adding or subtracting this vanishing cycle to any other cycle. So I thought I wrote it here, but I did not. Well, just maybe a smaller remark. So this Kashivara theory is somewhat undeservedly forgotten, because you may argue about its nature, and I, for instance, like to see it as a removable singularity theorem, because what it says that if something is true about small loop about a non-singular point, and small loop about around a point on codimension 1 subvariety, then the same would be true for any other small loops around other very degenerate points. So it is like a forced continuation theorem. So we know this such type of results from analytic functions of several variables, that if you have an analytic function, say, which is bounded over complement to a set of codimension 2, then it is also analytically extendable to the set of codimension 2 and higher. So this is the theorem in this spirit, and well, I dream of one day to discuss simple proofs of this theorem, since it is indeed a keystone of the topology of polynomials. And now I can formulate the main result, which is the theorem that we proved together with Galbin-Yamini and Dmitry Novikov. So we have a Pfaffian system, which is integrable, that solutions exist, which has a regular singularity on the singular locus, on the polar locus, which we also have for free because of the construction and of the Picard-Lefschetz of the period matrix. And in addition, it has quasi-unipotent monodromy along all small loops. So there are two analytic conditions and one topological condition. Then the claim is that in this case, the number, the upper bound that I already introduced, will be finite. That's the bound is uniform over all elements that you can choose in this situation. By itself, this result is not would not be very difficult because it's actually very much like analytic extension of certain finiteness results, say uniqueness. So if there would be no polar locus, no singularities, then the result will be, of course, just a consequence of compactness and analyticity, because the uniqueness theorem shows that on a compact set, an analytic function can have only finitely many zeros, and if it depends on parameters on a compact space, then the number of zeros will be uniformly bounded on those parameters. So the whole point was to extend it to the singular locus, but the problem is that we had to find an extension that would be explicit, efficient, that would be would allow to write an explicit bound, and we found such a way. I will talk about this in the second half of my talk, and it says the following: suppose that in addition, my system is defined over Q. So I said that it depends, the matrix depends on gamma, that's on the coefficients of the Hamiltonian. And I assume that this dependence is with rational coefficients. And having rational coefficients, we can look at the height of this matrix. That's the largest natural number that you need to write down all rational fractions which enter this matrix. And then the answer is explicit. So it is some double exponential bound, which depends on the height in the polynomial way, and all other parameters, dimensions and degrees, in a polynomial way as well, but on the second floor. So it's double exponential. And so this is some explicit polynomial of degree at most 20. Okay, so here I will probably skip application of this result to the infinitesimal Hilbert problem. Just wanted to say that the monodromy metrics associated to going around a point on the regular stratum is the Picard-Fuchs formulas, which has units on the main diagonal and plus minus one here, which means adding or subtracting the vanishing cycle. And this matrix is, of course, quasi-unipotent because both eigenvalues are ones. And ones are definitely on the unit circle. And now I will talk a little bit about the engine. So the engine is a quantitative study of higher order linear differential equations. So how we get to those equations? So we take our Pfaffian system and we take any line on which we are going to restrict it. Then everybody knows that after this restriction, the Pfaffian system becomes a system of first order ordinary differential equations with a matrix of the coefficients A of t, rational. And any such rational metric system can be reduced to a scalar higher order differential equation for each of the components, or for all linear combinations of the components. So this is the idea that you derivate, say, any linear combination which you need, linear combination of entries of x in T, and then you differentiate as long as you have a linear dependence over the field of rational fractions. So this is a pure differential algebra, or elementary differential algebra argument. So from the very beginning, we switch from Pfaffian systems to higher order differential equations. Now, those differential equations have rational coefficients, but this equation is homogeneous, so there is zero at the right-hand side. So we can get rid of the denominators and write it down in the following polynomial form. So pi will be polynomial coefficients without all mutually prime, so having no common roots that would be cancelled. And the leading coefficient is not identically zero, because otherwise we would just have an equation of smaller order. And as before, we see that we now will look at all such differential equations, and they are again parameterized by points of the projective space. And every time I'm happy about projective space for one simple reason: it is compact. So whatever I have in the projective space, which is locally bounded, will be globally bounded, and you can do a lot many things with this. So here, where is this projective space? All coefficients are defined modulo a common non-zero scalar constant factor. We can multiply all of pi by 2 or divide by 2. The equation will not be changed. And now we want to develop a paradigm, or to study results of the form. So if you know a differential equation, high order differential equation, can you say something about the number of isolated roots of its solution? So you see that here we instantly have a linear space of solutions, because solutions of every equation form a linear space, and we are asking for the uniform bound over zeros of all such solutions. And of course, what you start from is the equation with constant coefficients. So we have a polynomial in one scalar variable, lambda, and you assume that the polynomials have degree 0. That's their constants. And then, of course, generically, you know that all solutions will be linear combinations of the exponents. Well, generically, I mean, until there is no resonances, until all exponents are distinct, pairwise distinct. In the resonant cases, you may have exponentials multiplied by some lower order polynomials. All those things are quite known to undergraduate students. And then it turns out that you can actually bound the number of solutions of a number of zeros of any solution in any bounded domain. So assume that you have a domain U on the complex plane which is bounded, so its diameter is a finite number. You mark all the roots of this characteristic equation. So you have a finitely many points which together form a finite set of certain finite domain. And then we ask how many isolated roots may have solutions. The answer is at most this number. That's the product of the two diameters times a coefficient which slightly depends on the order of the differential equation. This is a simple theorem, although it is, we proved it together with Askold Khovansky I think 15 years, oh, not 15, excuse me, 25 years ago. And this is simple and elegant. So if I rephrase this result in the following way, then I would say the following, that we should compare non-leading coefficients with the leading coefficient. So an equation is bad, its solutions are strongly oscillating, if its non-leading coefficients are large compared to the leading coefficient, which in this case is equal to 1. So what you should do if you want to write this in the homogeneous case, you just have to take absolute values of the non-leading coefficients and divide it by the absolute value of the leading coefficient. So this is the homogeneous expression of degree 0 on the projective space, and it gives us an upper bound for the number of solutions. We call it slope. Well, I did not define it yet. Okay. What is what can be actually proved is a result in this period, which is true not for equations with complex coefficients, but also for equations with variable coefficients. So assume now that our coefficients are variable, but all of them are bounded in our domain U. And the leading coefficient is non-vanishing in U, which means that there are no singular points, because roots of P0 are exactly singular points of the equation. So then we can form this ratio, and it will be a relative magnitude of the non-leading coefficients. Once again, to get an say quick memory card. So an equation with bounded coefficients can be considered as a perturbation of the equation which consists of only the leading term. The equation which has only the leading term is very simple. The highest derivative is equal to 0. It will give us polynomials. And polynomials, of course, you know how many zeros they might have. The claim is that if you have a bounded perturbation, then the answer remains still bounded. And so this upper bound is in terms of the magnitude of this perturbation. So what are the two abstractions to extending this result for counting all zeros? First, we have still singular points. And second, unfortunately, even if we do exclude specifically equations with vanishing leading term, we can have the situation when this leading term is non-zero but uniformly very small. And so this expression mu would tend to infinity as some internal parameters tend to certain bad values.
Sergei, one question. So in this example, the infinity is non-regular. So this theorem is in general for linear differential equation. You don't assume any regularity of singularities.
No,
or
well, as I see, whenever I write down diameter in the affine chart, then of course I do mean that I am away from the singularity.
Okay.
So this is a very affine statement. It is not conformally invariant in any case. So now just a crash course about singularities. Singularities can be tame and wild. And this dichotomy is very simple. Either solutions grow exponentially or they grow moderately. And it turns out that you can distinguish the two cases without solving the equation. You just have to compare certain orders of zeros of the polynomial coefficients. This is the formula which nobody remembers, so it is maybe some advanced chapter in differential equations 1 or 2, but the point is that nobody remembers this formula, me included, because the right way to formulate this condition, it's called the Fuchs condition, which guarantees you that so all singularities are moderate. Instead of writing the differential operator in powers of like this, a0 dr plus a1 dr minus 1 plus and so on equal, equal to, sorry, I write a differential operator like this, and here d is d over dt. And ai are ai of t variable coefficients. And t equal to 0 is my singularity. And a of t are all holomorphic at t equal to 0. So the problem is that with singularity is that the order of root of a0 is larger than order of the roots of all our other coefficients. So instead of remembering those orders, you need instead to re-expand it in terms of the Euler operator, which is d over dt. So if we write this re-expansion for systems, then we just have to say that the matrix A has a first order pole, because here we'll have t d over dt x, and here the holomorphic matrix, holomorphic analytic, which means precisely that the order of the pole is 1. And for the same reason, we can re-expand our linear equation, higher order equation, in terms, in powers of the Euler derivation. Of course, we can get some denominators. We cancel them as usual because using the homogeneity of the equation. So we always get rid of the common denominator. And then the claim is that the leading coefficient will be 1, could be made 1. So the Fuchsian condition is the non-singularity assumption, but with respect to the Euler derivation, which means non-singularity in the logarithmic chart, because the natural variable, so time variable associated with the Euler derivation is the logarithmic time. And here is the main reason why I need equations and not systems of first order equations. That for systems, Fuchsian condition, moderateness, is sufficient for the tameness of the singularity, but not vice versa. For equations, this is equivalent. So if for some reasons I know that solutions of my equation behave nicely, then I get actually a lot of information about the relative orders of the coefficients on the singular locus. That's what I will need. Well, here is the toy case, which is basically the same equation with constant coefficients, but with respect to the Euler derivation. So in this case, well, I won't repeat the situation. I will just say that we have a polynomial in one variable, monic polynomial with a coefficient 1. And the differential equation appears when we plug the Euler derivation instead of the variable mu. And the characteristic equation will be just P of mu is equal to 0. And it has characteristic roots. And in the same way as the exponentials were forming a fundamental systems of solutions, in the constant coefficients case, here we have fundamental system of solutions made of powers, finite powers of t. And each such finite power is a multi-valued function, but it is of moderate growth, even if mu I are negative or non-real at all, the growth is moderate. And The only thing that we need to add in this case is that uniform upper bounds require that all characteristic exponents would be so in order to measurize the number of solutions, of roots of solutions, we need that all mu k be real. Why? Because this is the same condition as if we would compare on the infinite line real exponentials with sines and cosines. If you have a linear combination of only real exponentials, then this family of functions would be Chebyshev, so-called, non-oscillating. You cannot produce many zeros no matter where by taking linear combinations. Once you allow a non-zero eigenvalues, you have instantly sines and cosines, and each of them would bring you infinitely many isolated zeros. So if we want to work not on a finite interval, but on the whole positive real line, then we need to add the assumption that all eigenvalues are real. Here is a result which is similar to what I just 5 minutes ago I mentioned when I talked about perturbation of the equations with constant coefficients. Any Fuchsian equation can be considered as a perturbation of its Euler part. The Euler part, which happens when you replace t equal to 0 in the corresponding extension. And the claim is that if all the roots are real, then in the same then the Euler part would be non-oscillating. It would have only finitely many zeros, and then the magnitude of the nonlinear terms will be an upper bound for the number of roots. Okay, I'm limited in time. Okay, so now I will consider only Fuchsian equations, meaning that the equations of which have only Fuchsian singularities on the projective line, including the one at infinity. And for such equations, I can introduce the number, which is, well, you are already familiar with this. This is the relative magnitude of non-principal coefficients, non-leading coefficients relative to the leading coefficient. So this is, again, a zero-order homogeneous expression. And we can choose any norm on the space of polynomials. So, for instance, just L infinity norm, L1 norm, results will be all the same. Theorem. If we have a Fuchsian equation, if we know that all its singular points are Fuchsian, if we know that all spectra, all characteristic exponents at all points are real, what do we need to know to count the number of roots of this equation? The answer is you need to know only the slope. If the slope is large, then your equation has large non-leading coefficients. And so it would be more oscillating than an equation with small slope. And once you have time, which you don't, to think about this formulation, you would instantly recognize what Hossein did before, that there is something fishy in this formulation. Why? Look at this notion of this slope. This notion is not invariant with respect to changes of the independent variable. Just suppose that we return back to the case of equations with constant coefficients. So my polynomials are constants. And then the slope is what we already had written it to be. It's the sum of non-leading coefficients relative to the leading coefficient. Suppose we made a linear change of time. Then the coefficients will change linearly, again, will get if power lambda to some power. But we can choose the limit lambda equal to 0 or lambda equal to infinity to make the slope as small as we like or as large as we like. So it looks like the theorem is impossible. I formulated is impossible because I can always do a prescale of the independent variable, make the slope equal to 1, and prove some universal bound, which simply cannot be true. Some equations really do have many zeros. So the explanation of this phenomenon is, of course, the fact that the equation with constant coefficients has a non-Fuchsian point at infinity. It has an irregular singularity at infinity because exponents, no surprise, grow exponential at infinity. And so the slope, the equation is non-Fuchsian. And I insisted that I would work only with the Fuchsian equations. Otherwise, I would say nothing. Then there comes a non-trivial result. Suppose you have a Fuchsian equation. Then you can actually a whole group of transformations, a Möbius group of transformations, which consists of conformal isomorphisms of the sphere. And then you can apply such transformations, changes of variables in the equation. This will be a complete mess because the change of variable involves denominators. So after you substitute them and use the Leibniz rules as many times as necessary, you will get some huge equation, some huge rational functions. Then you would have to get rid of the denominators and then reduce them back to the polynomial form. And you simply cannot control what's going on with this your equation, except that you know that you can prove that the result will be uniformly bounded. So no matter which Möbius transformation you apply, you cannot change the slope more than by a constant and explicit factor. To see this, just note that if you take a Euler equation, which has constant coefficients with respect to the Euler derivation, then the linear changes t goes to LT is preserved the equation. So the logarithmic derivative will be the same. And this somehow explains why the slope can be changed, but only in a limited way. And well, this observation is actually the key to running the engine. So how we prove the main theorem, we reduce the Pfaffian system to a very multi-parametric system of equations. We notice that those equations are all uniformly Fuchsian, no matter how you restrict them on which line we want. And then you just make an observation that if your polynomials are defined by over Q, and if you control the complexity of the process, how they appear. So initially they were some polynomials of controlled height. Now you do with them lots of various operations, including rescaling, including desingularization. But the complexity of this process is under control. I cannot predict the result, but I can predict how many times need I have to multiply, divide, and so on. And then I get an explicit bound on the slope. So that's the conclusion. What we proved is that periods form a special class of analytic functions, which, despite being transcendental, exhibit certain polynomial or rational type behavior. They admit counting zeros, their zeros, in the way the zeros of multivalued functions could be counted. So there is sort of Bezout theorem. You can consider this as an algebra, extension of algebra to some transcendental functions, in which you still have something like a Bezout theorem. You look at the formula of the Pfaffian matrix. You count the bytes, how many you need them to. You need to write it explicitly in the LaTeX file, and then knowing the size of this file, you can predict an upper bound for the number of zeros. So, obrigado pela sua atenção.
Okay, thank you, Sergei. Okay, any question in the recorded session? Maybe, okay, I will ask. I have one question. If you replace triangle with passes which are allowed to turn around singularity, let's say m times, I mean, you define it in a proper way.
The result will be true, and that's actually what happens to do, because sometimes in the process we need to desingularize, and then your triangles stop being triangles.
Yeah.
And if you make a conformal transformation, your triangles will be no more straight side triangles, but say things, as long as you have a subdivision of the projective line into semi-algebraic subsets of controlled complexity, you can do this. You can actually easily reduce bounds for triangles for bounds on any other objects, but of limited complexity. So, for instance, you can allow for 10 turns around the singular point, but you cannot prove a uniform bound when 10 tends to infinity.
Yeah, but this upper bound depends on this number 10 or the number of turns?
Of course it will, but...
how it depends? It is polynomial?
It's most likely polynomial.
Okay.
Most likely polynomial, but here my problem was completely opposite. So the problem has too many parameters. And so I tried to reduce the number of parameters to as few as possible. You certainly do have parameters which are essential. That's degrees and dimensions. It turns out that there is only one extra parameter that can control all the rest. That's the height of the numeric height of the Pfaffian system. So this is a number theoretic, if you wish, ingredient in the whole construction.
Okay. Okay. So let me just stop recording so the people feel comfortable to ask questions.